In the quiet dawn of September 1st, 1859, the world was unknowingly on the cusp of witnessing a celestial event unlike any in recorded history. Above Earth, on the blazing surface of our sun, a violent eruption was about to send a storm hurtling through space, its effects destined to rattle the very foundations of human technology. This was the day of the Carrington Event, the most powerful solar storm ever documented, named after Richard Carrington, the British astronomer who, by chance and curiosity, witnessed the violent flare as it exploded. Carrington, sitting at his telescope in London, was among the few who observed the sun's sunspots, dark blemishes on the solar surface that heralded magnetic unrest. On that day, he saw a sudden, brilliant flash, a searing white light exploding from one of the largest sunspot groups ever recorded. The flare lasted only about 5 minutes, but it was the violent prelude to an enormous coronal mass ejection. A colossal cloud of solar plasma and magnetic fields blasted into space at breakneck speed. This storm of charged particles would traverse the 93 million miles to Earth in less than a day, a journey that typically takes 3 to 4 days. At the time, human technology was only beginning to rely on electricity, and the telegraph had become the first global communication network. Across Europe and North America, telegraph lines threaded through cities, towns, and rural landscapes, transmitting messages with electrical pulses along copper wires. Yet, these wires unwittingly transformed into conduits for the sun's invisible fury. As the solar storm slammed into Earth's magnetic field, it induced intense geomagnetic currents in the ground and the atmosphere, surging through telegraph cables, damaging equipment, and setting the stage for unprecedented electrical chaos. When the storm hit on the night of September 1st and the following day, auroras erupted far beyond their usual polar confines. The night sky lit up with vivid curtains of green, red, and purple light, visible as far south as the Caribbean, Hawaii, and even Rome. The shimmering auroras were so bright in places like the northeastern United States that people reportedly read newspapers by their glow at midnight. This spectacular light show was the dramatic manifestation of particles colliding with Earth's magnetic field, a visible reminder that our planet was connected intimately to the sun's activity. Meanwhile, the telegraph system, the marvel of 19th century communication, was thrown into turmoil. Telegraph operators encountered strange surges of electricity strong enough to shock them and even ignite fires in some cases. Reports tell of sparks flying from telegraph machines and some operators continuing to send and receive messages despite having disconnected their batteries, powered purely by the storm's geomagnetic energy. Lines buzzed, machines smoked, and communication ground to a halt in many areas. Although telegraph networks soon recovered, the event exposed a vulnerability that few appreciated at the time. In retrospect, the Carrington Event was a cosmic reminder of just how volatile and interconnected our solar environment can be. It was a solar superstorm, a perfect storm of a powerful solar flare and a fast-moving coronal mass ejection colliding with Earth's magnetosphere with explosive effect. While it dazzled the sky and disrupted primitive technology, it caused no lasting harm because the world's electrical infrastructure was still in its infancy. But it was an ominous warning that the sun was capable of much more. The science behind this event is complex yet fascinating. The sun's surface is a roiling magnetic cauldron. Sunspots are regions of intense magnetic activity where magnetic field lines twist and break, releasing vast amounts of energy in the form of solar flares, bursts of light and radiation across the electromagnetic spectrum. Often accompanying these flares are coronal mass ejections, CMEs, massive expulsions of plasma and magnetic fields launched into space. When a CME hits Earth, it compresses our planet's magnetic field and injects charged particles into the magnetosphere, causing geomagnetic storms. Earth's magnetic field acts like a shield, protecting us from the solar wind's continuous flow of particles. But when struck by a CME, this shield is temporarily distorted and overloaded. The charged particles spiral along magnetic field lines, entering near the poles and interacting with atmospheric atoms to produce auroras. At the same time, these interactions induce powerful electrical currents in the Earth itself, known as geomagnetically induced currents, GICs, which can infiltrate electrical grids and infrastructure. The 1859 storm was exceptional because of the speed and intensity of the CME and the strength of the geomagnetic storm it triggered. Today, scientists estimate that the Carrington Event's geomagnetic storm reached a disturbance storm time DIST index of around -850 nanoteslas, an indicator of extreme magnetic activity. For comparison, typical geomagnetic storms reach a few hundred nanoteslas. This made it the strongest geomagnetic storm ever recorded in modern history. For decades, the Carrington Event remained a fascinating historical footnote. But in the modern era, as society has become increasingly reliant on electricity and digital infrastructure, the potential damage from a similar event has become a subject of serious concern. Satellites orbiting Earth, GPS navigation systems, electrical power grids, undersea cables, aviation communication, and even financial networks depend on a complex web of electronics vulnerable to electromagnetic interference. Unlike the 19th century, today's technology would not just falter, it could collapse under the stress. If the same solar storm struck now, the consequences could be catastrophic. Modern power grids are vast, interconnected systems spanning continents, with high-voltage transformers and long transmission lines susceptible to geomagnetic currents. Unlike telegraph wires, these power lines are grounded and far more efficient at conducting induced currents, which could cause widespread transformer damage, blackouts, and grid failures lasting months or even years. Moreover, the digital world relies heavily on satellites. Communications, weather forecasting, television, internet connectivity, GPS for navigation and timing, military operations, and even banking systems depend on satellites orbiting above Earth's atmosphere. Solar storms can fry satellite electronics, disrupt signals, and cause temporary or permanent loss of function. In 1989, a much smaller geomagnetic storm caused a 9-hour blackout in Quebec by knocking out transformers. Imagine that, but on a continental or global scale. The specter of a Carrington-level event raises profound questions about preparedness. Governments, utilities, and scientists around the world now study space weather with growing urgency, deploying satellites and ground-based monitoring systems to provide early warnings. Yet predicting the exact timing and magnitude of solar storms remains challenging. Mitigation strategies, such as hardening infrastructure and developing rapid response protocols, are in progress but still incomplete. The 1859 Carrington Event remains a stark lesson etched in history. A powerful reminder that the sun's immense power can reach across millions of miles to disrupt human civilization. What was once a curious incident in an era of telegraphs is now a looming existential threat to a world transformed by electricity and digital technology. As humanity stares upward at the blazing star that sustains life, it must also prepare for the possibility that the sun's next great tempest may rewrite the rules of survival on Earth. Imagine for a moment waking up one ordinary morning to a world suddenly plunged into darkness. Not just a brief blackout, but a widespread, prolonged loss of power. In this world, every blinking light, every glowing screen, every humming server farm that powers the digital lives of billions has been silenced. The hum of electricity, the pulse of information, the constant flow of data has vanished. This is not the result of a cyber attack, a terrorist strike, or a natural disaster like a hurricane or earthquake. Instead, the culprit is a force as ancient and powerful as the sun itself, a solar superstorm, a modern-day Carrington Event, barreling toward Earth. Our modern civilization depends on an intricate, interwoven web of electrical and digital infrastructure that underpins nearly every aspect of daily life. It is a marvel of human ingenuity. Vast power grids spanning continents, global communications networks connecting continents in milliseconds, satellites orbiting Earth and enabling navigation, weather forecasting, and communication, and an entire financial system relying on electronic data transmission. Yet this network is fragile in the face of nature's most extreme phenomena. If a storm like the Carrington Event were to hit today, the consequences would be devastating, reverberating through every layer of society. At the heart of the danger lies the electrical power grid. High-voltage transformers, the critical nodes that step up and down electricity for distribution, are particularly vulnerable. These transformers are massive, expensive, and not easily replaced. When a geomagnetic storm strikes, it induces powerful electric currents in the ground that travel into power lines and overload transformers. Unlike the simple telegraph wires of the 19th century, today's power grids cover thousands of miles, creating extensive pathways for geomagnetically induced currents to flow. This can cause transformers to overheat, short-circuit, or even explode, leading to cascading failures across the network. Power outages caused by such damage wouldn't be confined to isolated regions. Entire countries or even continents could experience blackout conditions. Unlike the brief outages caused by storms or technical failures, recovery could take months or years, as transformers are custom-built and manufacturing capacity is limited worldwide. Without power, modern hospitals would lose vital life support systems. Water treatment plants would shut down, risking contamination. Transportation systems would grind to a halt, and communications, cell phones, internet, emergency services would cease functioning. The modern world's reliance on electricity means that such an event would effectively paralyze civilization. But the power grid is only one part of the story. Above Earth, satellites that enable GPS navigation, weather monitoring, telecommunications, and military reconnaissance would face their own peril. Solar storms bombard satellites with intense radiation and charged particles that can damage electronics, disrupt onboard computers, and degrade solar panels. In some cases, satellites are temporarily blinded by energetic particles or permanently disabled. This loss would create cascading failures in everything from airplane navigation and ship routing to financial transactions and emergency response coordination. A solar superstorm could also cripple communication networks on the ground. Fiber optic cables themselves are not vulnerable to geomagnetic currents, but the repeaters and amplifiers that maintain signal strength across vast distances rely on electrical power. Without electricity, the backbone of the internet could fragment into isolated pockets. Data centers housing the servers that power cloud computing and online services depend on uninterrupted power and cooling systems, both vulnerable in a blackout scenario. Transportation would become chaotic. GPS systems that guide everything from commercial flights to everyday cars would lose accuracy or fail entirely. Air traffic control would revert to manual operations with reduced capacity, increasing the risk of accidents. Shipping companies dependent on GPS for precise routing would face delays and increased costs. Even trains relying on electronic signals for safety and scheduling would be at risk. Beyond immediate infrastructure, the economic impact would be staggering. The global economy moves on data transmitted through electric networks. Stock exchanges, banking systems, and payment processors depend on instantaneous connectivity. In the absence of reliable power and communications, financial markets could freeze, transactions would be delayed, and confidence would collapse. Supply chains for food, medicine, and fuel could break down, leading to shortages and social unrest. Emergency services and government response would face unprecedented challenges. Without electricity, hospitals would rely on backup generators, but fuel supplies might be limited. Communication between agencies would be hampered, coordination delayed, and public information scarce. In such a crisis, panic and confusion could spread quickly, magnifying the human toll. The social fabric itself would fray under these pressures. People's everyday lives revolve around technology that a solar storm could render useless. The loss of refrigeration, lighting, heating, or cooling, and sanitation would compound physical discomfort with psychological stress. The sense of disconnection, unable to reach loved ones, to access news, or to perform normal activities, would deepen feelings of isolation and fear. While the scenario is grim, the modern world is not entirely defenseless. Scientists and engineers have developed early warning systems that monitor solar activity and can provide alerts hours or days before a solar storm arrives. Space-based observatories and ground stations track solar flares, coronal mass ejections, and geomagnetic disturbances. This gives utilities and governments precious time to prepare, disconnect vulnerable systems, reduce loads on transformers, and activate emergency protocols. Efforts to harden infrastructure include installing devices that can block harmful currents, redesigning transformers to be more resistant, and creating redundant systems that can operate independently. Satellites are built with shielding and fail-safes to withstand radiation, and critical systems have backups that can operate in isolation. Governments have begun incorporating solar storm scenarios into disaster preparedness and response plans, coordinating across agencies and industries. Yet many experts caution that despite these advances, the scale of a Carrington-level event poses extraordinary risks. The interconnected nature of modern systems means that failure in one sector rapidly spreads to others. While individual components may be protected, the systemic vulnerabilities remain. The question is no longer if such an event could occur, it will eventually, but whether society is prepared to absorb the shock. The lessons of the past are clear. The Carrington event was a natural phenomenon of staggering power, and it nearly overwhelmed the primitive electrical technology of its day. Today, that technology is foundational to modern life and orders of magnitude more complex and fragile. The sun's fury, once a distant curiosity, now threatens to tear through the digital fabric that connects the globe. As the sun continues its 11-year solar cycle, with peaks of activity bringing more frequent flares and storms, scientists watch and wait. Space weather forecasting is improving, but remains imperfect. The possibility of a devastating solar superstorm is real, looming like a shadow over the digital age. In this fragile balance, humanity faces a paradox. We owe our civilization to the power of electricity and the connectivity of digital networks, both gifts of modern technology and vulnerabilities in the face of cosmic forces. The sun, the source of all life and energy on Earth, can just as easily disrupt or destroy the infrastructure upon which we rely. The next Carrington event could bring the modern world to its knees, forcing a reckoning with the limits of our technological progress and the need to respect the volatile star that watches over us. The storm has passed, but the world it leaves behind is unrecognizable. The sun's wrath, unleashed in a torrent of charged particles and magnetic fury, has ripped through the digital arteries of civilization. Cities lie dark, communication lines are severed, and vital infrastructures crumble under the weight of disruption. This is the aftermath of a modern-day Carrington event, a catastrophic solar superstorm whose impact reverberates far beyond the flicker of flickering screens or the hum of silent power lines. It is a test of human resilience, ingenuity, and determination to rebuild. In the hours after the storm, the magnitude of the destruction becomes painfully clear. Transformers that once hummed steadily with electric current now lie fried and useless. Power grids, vast networks spanning countries and continents, have fractured. Blackouts stretch across cities and rural areas alike, with no quick fix in sight. Repairing the damage is a logistical nightmare. High-voltage transformers are not only costly, but require weeks or months to manufacture and install. The specialized components needed are sourced from a handful of factories worldwide, none of which are prepared for such sudden demand. Without power, hospitals struggle to operate on emergency generators, whose fuel supplies dwindle rapidly. Refrigeration for medicine and food ceases, threatening the health of millions. Water treatment plants fail, endangering drinking water and sanitation. The loss of heat in colder climates or air conditioning in hotter ones adds to human suffering. Transportation networks halt as traffic lights and signaling systems lose power. Roads become clogged with stalled vehicles, and public transit grinds to a halt. Communication, a lifeline in any disaster, is largely gone. Satellite systems, damaged by intense solar radiation, flicker in and out or go silent entirely. Cell towers without power become useless. The internet fragments into isolated pockets where backup generators or unaffected local systems remain. Emergency responders struggle to coordinate, hampered by lack of communication and the sheer scale of the crisis. Without reliable news or information, misinformation and panic spread among the population. Yet amid this darkness, resilience begins to stir. Communities rally together, sharing resources and information. People revert to analog methods. Landline phones were available, radios powered by batteries or hand cranks, printed maps and paper records. Emergency services and government agencies activate contingency plans. dispatching teams to repair critical infrastructure and maintain order. The recovery effort is unprecedented. Governments declare states of emergency, mobilizing National Guard units and the military to assist with security and logistics. International aid flows in, but coordinating relief is complicated by damaged communication and transportation. Specialized crews travel to affected sites, working around the clock to replace transformers, repair transmission lines, and restore power in prioritized regions such as hospitals, emergency centers, and water facilities. The scale of economic loss is staggering. Without electricity and communication, factories halt production, supply chains break down, and markets freeze. Financial systems strain to operate, with banks closing branches and ATMs offline. The loss of digital payment systems forces a return to cash transactions where possible, creating shortages and delays. Global trade slows dramatically, compounding shortages of essentials like food, medicine, and fuel. Insurance claims skyrocket, and governments face enormous costs for recovery and compensation. But beyond the material losses, the social impact runs deep. The blackout disrupts education as schools close or shift to improvised methods. Workplaces shutter, pushing millions into unemployment or forced leave. The psychological toll mounts as uncertainty, fear, and isolation weigh heavily on individuals and communities. The slow pace of recovery tests patience and trust in institutions. Governments and utilities face intense scrutiny for perceived unpreparedness or failures. Yet the crisis also ignites innovation and adaptation. The disaster forces a reckoning with vulnerabilities long overlooked. Policymakers and engineers seize the moment to overhaul infrastructure resilience. Investments pour into research for more robust power grids, including underground cables less susceptible to geomagnetic currents, smarter grid management systems that can isolate and protect vulnerable sections, and rapid response teams trained specifically for space weather emergencies. Satellite technology evolves, with new designs incorporating enhanced shielding, redundant systems, and rapid reboot capabilities to withstand radiation storms. Backup communication networks, such as high-frequency radio and mesh networks, are developed to provide emergency connectivity independent of satellites and traditional infrastructure. Space weather forecasting improves, utilizing constellations of solar observatories to provide earlier, more accurate warnings. On a societal level, communities adopt a culture of preparedness. Education campaigns teach the public about solar storms, emergency supplies, and alternative communication methods. Governments integrate space weather into national disaster response frameworks, coordinating across agencies and international borders. The realization dawns that while the sun's fury cannot be prevented, its impact can be mitigated with foresight and cooperation. The recovery from such a storm would not be quick or easy. It could take years for full restoration of infrastructure and services, reshaping economies and societies. But humanity's history is marked by resilience in the face of natural disasters. From earthquakes and hurricanes to pandemics and wars, societies have rebuilt, learned, and adapted. The solar superstorm, though a unique and daunting challenge, is part of that continuum. Ultimately, the Carrington Event stands as a profound reminder of our place in the cosmos. The sun, a source of life and energy, wields immense power that can disrupt the most advanced human creations. It teaches humility and respect for natural forces far beyond our control. It urges preparedness, scientific inquiry, and international collaboration to safeguard the technological marvels on which modern life depends. As the digital world slowly flickers back to life, powered by repaired transformers and restored satellites, a collective resolve takes shape. The storm that once threatened to silence civilization becomes a catalyst for resilience, innovation, and unity. The challenge remains vast, but so does human ingenuity. And beneath the glowing sun, life endures, ever adapting to the cosmic dance of light and shadow.